Hold on with that other hand. Yeah. Thank you, though.
Yeah.
All right.
Last year is good down that. Or it was 2 years ago, whenever it happened.
All right, guys, I don't know what page this is for you, but can you turn to this? Somebody tell me what page this is for you guys. 81? Okay. Well, man, you Friday. Got a 3-day weekend coming up.
Yeah.
It's been a long week. You just missing one?
Wow.
1, 2, 3, 1, 2, 3, 4, 4. Okay, just missing Addison. All right, guys. I guess I can answer questions. Anybody have a question on anything we're doing, a problem? I've been noticing errors in the book. Like there was a problem, and I'm noticing them from the next chapter we're going to head towards. But if you see errors, or like I think I made a key once, I did the wrong problem. I think I assigned you 32, but I did 33 or something like that. And for the record, that particular problem looked something like this. It was some function, and I think it was x to the 2.4 plus e to the 2.4. What's the derivative of that? 2.4x to the, then what? Everybody know that that's it? I'm seeing some looks like, yeah. But like, not a lot of confidence. Remember, what is e? It's a number. So a number to a power is just a big constant, right? Well, maybe not a big constant, but it's a constant. And derivatives of constants are 0. So remember, if you see an e or a pi, or stuff like that, that you know stands for a value that's a constant, then the derivative of a constant is 0. So you would stop right there. All right? Thought I'd mention that. Because that's a sucker play. Like I give problems like that occasionally, just to check to see what you're doing. Like I'll say f of x equals 2 pi cubed. What is f prime of x? And you got to know that that's 0, right? Don't go 6 pi squared. If you really do the chain rule, remember how the chain rule, technically, you go back and take the derivative of the, like, you know how on the chain rule was something like this? Even though we talked about this, but even though I don't really write it, the derivative is 12 blah squared times the derivative of the blah. What's the derivative of x? 1, but you don't have to bother writing the 1. But if I did that here, I would go 6 pi squared times the derivative of the pi, but what's the derivative of pi? 0, which would make all that go away. So technically, you could still do a power rule, but the chain rule that we ignore for a single x would have cleaned all that up. But most people wouldn't catch that. They would just write 6 pi squared if they're not really on their game. So remember, pi and e are numbers. Don't let that get you. Anybody else on anything derivatives that we've talked about? Yeah. And you'll have to give it to me on my book.
It's like on the homework class sheet. It's like you got over number like 20.
This one right here?
Yeah.
Okay. And 21 also?
Yeah, just 'cause,
Okay. Yeah, so number 20, you have a natural log of something. So I'm going to ignore that something for now and just treat it like the blah, like natural log of blah, and then I'll come back and catch it on the chain rule. So the first thing I do is say, what is the natural log derivative? Well, the derivative of a natural log, the way we've been doing it is you just basically copy whatever you're logging to the denominator. And that takes care of the derivative. And the only thing left is to go back and do the chain rule. Now, I could put a 1 there and go times and then do the chain rule, but it's going to end up when you clean it up in the numerator anyway. So I just then take the derivative of that. So what's the derivative of the 1? 0. And then what's the derivative of e to the 2x? What's the rule on e? Copy it down. And that takes, you've already done the 1. That takes care of the e part. And then what's the derivative of the 2x? So times 2. And there's really nothing much more you can do with that. You maybe move the 2 in the front, but it's fine like that to me. And then over here, I'm going to show you 2 ways to do this. One way is to just do it exactly like you see it. Another way is to maybe before you start, think about that as a t to the negative 2. It doesn't matter. You got to be familiar with your answer. It's probably, if this problem showed up, it would be a multiple choice question, and you're going to try to make your answer fit one of those options anyway. But if I'm doing it this way, I go, well, the derivative of t squared is 2t. And then I'm looking at that and I'm seeing a quotient. All right, so I put a plus like I did, and I go, what's the quotient rule? It's a fraction with what? Low d high. So I would write the low, except what's the d high? 0. So do I need to write any of that? So I'm not going to. So the low derivative of the high is 0. So all that's going to go away. Then I'm going to go minus the high derivative of the low. Well, what's the derivative of the low? 2t. So that times 2t over the low squared, which is t to the 4th. Now, what's negative 2t over t to the 4th? One of those t's would cancel, wouldn't it? And I would end up with this if I was cleaning that up. I guess you could technically really clean it up by finding a common denominator. And again, I don't know what they're going to do on an AP test. They change from year to year. But if I put an extra t cubed on the top and the bottom, it is possible that they might have you clean it up like that, but it's doubtful. AP is really not that big on cleaning up their answers. It's shocking what they will accept as an answer, especially in the free response. So on the multiple choice, they're not going to do a whole lot of form changing. I mean, they might clean it up a tad, and you'll see some of that, but they're not going to, I doubt you would ever see anything like this. It would probably be what you saw here in the red. All right, so I'm going to get rid of most of that blue stuff so we could focus in on the red. Now, the other option is, and a lot of people would rather do this, and I just get 2t minus 2t to the negative 3. But if you see that t to the negative 3 is the same thing as that is. So that's probably a little cleaner, but whatever. Yeah.
Can we leave it like that, or do you want to?
Sure. Yeah. You got to unlearn a little bit about what we brainwashed you with in Algebra 2 and Pre-Cal. No negative exponents, whatever. Rationalize your denominators, whatever. You really got to unlearn some of that because nobody really cares. Now, again, if this right here is what you got and this is the answer on the key, definitely be able to understand that, oh, well, not maybe the key, but like on a multiple choice test, make sure that you understand, oh, yeah, that's the same thing. But as far as free response, I don't care how you leave it. Negative exponents, fractional exponents, you don't have to change like a 1/3 power back to a cubed root. Don't bother because most of the time you're going to see it as a 1/3 power. All right? Yeah, I really don't know why, honestly, that Pre-Cal and Algebra 2 are so intent on a lot of that simplification. I don't. Because when you get to other orders of math, they just don't seem to care as much. Now, that may not be true at the college level anymore. I don't know. You'll have to get there and see. But it's good to know that stuff because a lot of times the answers are simplified. So know it, but don't worry about it as much. Anybody else on any of this? 15? Right here? Okay. I need to talk. I don't know. I keep forgetting on third period. I want to talk to you about a shortcut for doing a square root because all of my keys have that. So you've probably been doing a square root a different way and you get your answer and like, what the heck is he doing? And maybe you noticed that you could simplify, but this shortcut is really great for square roots. Now there's shortcuts for cube roots, fourth roots, fifth roots, for all of them. But for some reason, AP never leaves their answers that way. They always do like if that was a cube root, they would change it to a 1/3 power. But for a square root, a lot of times they're going to do what I'm about to show you. So I'm going to basically do this with a 1/2 power, and then I'm going to simplify it, and then I want you to tell me what the shortcut is. So this is what I would do if I did not know my shortcut. I'd come in here and go, well, not a big fan of that square root, so I'm going to change the square root to a what? A 1/2 power. Okay, so it's that to the 1/2. So the derivative now tells me to go 1/2 blah to the negative 1/2, and then that takes care of the 1/2, right? And then the chain rule says come back now and take the derivative of the blah. All right? Now, if I were to simplify this, which means I don't want a negative exponent and I don't want a fractional exponent, what would this look like? Well, clearly there's a negative exponent, which means to take that and do what? Put it in the denominator. So I'm going to go ahead and draw a denominator, and I'm going to take that and put it in the denominator. That's what the negative does. But what does the 1/2 do? Changes it back to a square root. So basically that means the square root of this in the denominator. All right, fair enough. That takes care of this. What does the 2 go? I mean, I could put a 1/2 up top, but if it's 1/2, doesn't the 2 technically go in the denominator also? That takes care of that. And then the 2x is not in the denominator. That's a numerator value. So that would go up here. Okay? Now, look at this. And look at my original problem. I'm going to rewrite the original problem. And tell me, what does it look like I did if this is the function to get the derivative?
2 times the square root of that in the
So it looks like I doubled that and put it in the denominator.
And then the derivative of the inside.
And the derivative of the inside part in the numerator. That feels easier. So from here on out, when you see a square root, just double it in the denominator, and then the square root of the derivative of the inside part in the numerator. Yep.
If there was like a multiplication like 25, would you just do that times like D1?
Yeah. So if I see this, when I'm looking at that, I'm like, well, looks like I got a product rule. So I'm going to go, because it's multiplication. So I'm going to go first D second plus second D first. But when I get to the D second, I'm going to insert that rule. So right here, I'm going to go, well, I am multiplying these two things. So first D second. But for the D second, I'm going to double the square root in the denominator, derivative of the inside part in the numerator. First D second. And then I'm going to go plus second, and then times D first. And it would probably look a little better if I put the 2x up front, but whatever. That's what my key would probably look exactly like that. So we'll learn about simplifying this. Like if I, most of the time, and you'll learn this next chapter, when you're taking a derivative, you're finding a slope. Well, we're going to use those slope because that's a slope equation, right? Right? So if I want the slope at 3, I just go now and plug the 3 in. Right? So like right here, if I want the slope at 3, I'm going to go 9 times. I got 18 on the top. I got 2 times 1 on the bottom. 3 in there gives me 3 times 9 is 27 minus 2 is 25. Oh, how convenient. Square root of 25 is 5. Then I come over here. Another square root of 25 is 5 times a 6. So I can clean some of that up, but not much. So I get 81/5 plus 30. If you're on an APCalc test, you know what? They would literally take this as an answer. Now, if it was multiple choice, they won't. They would take that as an answer. Believe it or not. I almost feel so uncomfortable leaving that, but they would take that. They're like, oh, we don't care about simplification. But now on a multiple choice test, you're going to have to be able to clean it up, right? So on a multiple choice, sure, you're going to have to clean that up and go 81/5 plus 30. Yeah, 5 on the top, 5 on the bottom. And you'd have to be able to get that 2/31/5. But anyway, what we normally do in calculus, and you'll see this next chapter, is we're trying to find things like relative maxes and relative mins. Relative max, relative min. What's the slope at a relative max? What's the slope at a relative min? So we're constantly taking these slope equations like this. We're taking that and we're setting it equal to 0. So a lot of people think, well, I got to simplify it. I got to simplify it. No, what you're probably going to be doing with that is solving. And to solve, we might add together. We might find a common denominator and multiply it through to clean it up. There's lots of things that we may do, but that whole traditional let's simplify it isn't always the best practice. So when we get to that next chapter, we'll take a look at what the best practice is, but you'll also find that you don't get as many ugly looking derivatives, because if it's super ugly, we might not even have the math to solve it. All right. But anyway, that's kind of where we're headed. We're going to be finding maxes and mins, and that's why this shows up in economics, and because there might be, function curves that represent growth of a company, their margins growth, their profits, their costs, and you want to minimize costs, maximize. So you run these, you get guys that run numbers and analyze these things and try to figure out, hey, what do we need to do to maximize the profit? And where would that occur? Like, how many units do we need to sell? And they use this information, but they use calculus a good bit. But anyway, whatever. Maybe they're using a program built on calculus. They might not be actually pulling out an integral and a derivative, but they might be. I mean, I remember my brother was a finance guy, and I remember his first job, he was working for W.L. Gore up in Flagstaff that makes Gore-Tex products, but they also do like liners, heart liners, and things that they, surgical stuff. And he was in their analytics department. He said, I use calculus every day, which is amazing. I mean, you wouldn't think if you're in a business application that you would see that much math, but you do. All right, so we're going to skip that average rate of change. I really don't know why I threw it in there. Is that on your homework tonight? Can somebody just tell me or go over it? Seems like that was later.
Yeah,
It is tonight? Is the average rate of change thing anywhere on your... For today? Okay, we may or may not get to it. If we don't worry about that sheet. I want to focus on trig stuff. Okay, so trig derivative notes. Who was it in here? Was it you said the other day? We would have taken your word for it when I was showing you this little proof or something. Okay, I'm going to show you a proof real quickly for why one of the trig rules works. One of the trig derivatives is what it is. And you're going to look at it and go, oh, same kind of thing. I could have taken your word for it. But I always wanted to know. Now, I don't want to know for all 6, but I want to know, oh, it kind of makes sense. And I think if I do it for sine, I think you'll buy it for cosine. Did I do it? Yeah, I did it for sine. And then I'm going to show you, once you prove sine and cosine, because all the other derivatives are based on sine and cosine, right? Tangent's sine over cosine. Cotangent's cosine over sine. Since all the other ones are, we could use the quotient rule to prove the other ones. So I just want to give you a glimpse as to why this works. It's very ugly. I mean, really ugly. You're not going to have to remember any of this. What you are going to have to remember is that the six trig derivatives are right here. You got to memorize them. And there, most people do. If you do enough homework problems, you'll have it memorized. If you don't do the homework problems, then you'll walk into the test like, I think I have them, and you'll get them messed up, and you'll miss every trig derivative because you have the basic information wrong. So check it out. And then I'll show you the proof. Derivative of sine of anything is cosine of that thing, and then the chain rule comes in and says times the derivative of whatever you were sining. Are you following me? So if I said, what's the sine of x squared? It would be cosine of x squared times the derivative of the x squared part, so times 2x. All right, cosine of u, the derivative is negative sine of u. Derivative of tangent is secant squared. So derivative of tangent blah is secant squared of the blah times the derivative of the blah. The derivative of cotangent is negative cosecant squared of the blah, derivative of the blah. The derivative of the secant of blah is actually the secant of the blah times the tangent of the blah, and then the derivative of the blah. And the derivative of the cosecant is the negative cosecant of the blah, cotangent of the blah, times the derivative of the blah. Now, do you notice any patterns? They all have du. That's the chain rule, right? So they're all going to have that for sure. What else? Which ones are negative? Which one have negative derivatives?
Oh.
All the cos. So the cosine, the cotangent, and the cosecant are all going to have negative derivative values. Okay? Now here's something else I noticed. It may help you. If you can learn this one, and you can learn this one, and you can learn this one, okay? If you have those down, like if you know sine is cosine, then the co of the sine, cosine, will have a negative cosine of this answer. You know how sine and cosine are considered co-functions? Tangent, cotangent, co-functions. Secant, cosecant are co-functions. So if sine and cosine are co-functions, their answers are co-functions, but this one's negative. If tangent and cotangent are co-functions, their answers are co-functions, right? Secant squared u, negative cosecant squared u, except the co has the negative. If the secant and the cosecant are co-functions, then their derivatives, secant tan, cosecant cotan, except, again, the co has the negative answer. So if you can learn the three I gave you that were underlined, then you can just go, oh man, I forgot cosine. Well, I know it's negative, but if I know sine is cosine, then cosine is sine, because it has a co-function answer. Co-function answer, co-function answer, except for the negative. But again, it's just a little whatever lame way to remember. But if you can't, if that helps, great. If it doesn't, the more you do them, the more you'll have them. But there's no shortcut for doing these. And this is the basic trig function. Trig function can have powers. The u part can have powers. There's a lot going on in a trig function. I can give you a little tiny trig function and say the derivative, and your derivative might be this long. You'll see this in a second. Okay? So let's walk through a real quick proof. And if you're like, I don't like the proof, you can la through this if you want. Just do it quietly. But really, I want you to kind of see it. All right? So here we go. If y is sine, then y is the derivative of y cosine. Okay, well, we have that definition of a derivative function, right? It is it's this right here. I didn't rewrite it, but we did it yesterday, right? The limit of f of x plus h minus f of x over h as h goes to 0, right? And if my function is sine, then I should have sine of x plus h minus sine of x over h. And that's what I wrote right here. Now you look at that and you're like, how the heck do I simplify that thing? Well, you got to pull out your alpha plus beta identity from pre-calc or algebra 2 maybe. You remember sine of alpha plus beta? No, do you remember doing it?
Yes. Yeah.
Trig identities. Surely you remember your trig identities at some level. Even if you don't remember them, you should remember doing them, whether it's a hate, love, whatever. Well, here's the formula. Sine of an alpha plus a beta was the sine of the first angle, cosine of the second, plus the sine of the second angle, cosine of the first. Okay? Well, I can replace that then with that function. So here I did. Okay, so there it is. I replaced that with that, brought the negative sign, the h, everything else down. Now at this point, I am going, well, I really don't need these parentheses. They're not doing anything. There's nothing out front to distribute. So at this point, why don't I take this and move it there, and this and move it there, because I can change the order when I'm adding. So I did that, and that's where I am right here. Then I just decided to regroup it. Why? So that I can now factor out a sine of x. Okay? Like, why did you factor out a sine of x? Well, at this point, I thought, well, I could put all of this, which is a big term multiplied, over an h. And I could put all of this over an h because there's a plus there. I can do that and break it up into two limits. So I did. That's what I see right here. Now, this is something I haven't mentioned yet, but I need to mention it a bunch for you to really log it in. But what's the variable here? Is it h or is it x or is it both? It's actually h. That's really annoying because we're so used to doing variables with x. In fact, almost every limit you saw, if not every limit you saw in your test, was as x approaches something, right? Because we're always dealing with an x and y axis. But on this one, if I ever take a limit with h is my variable, which means what would x be? Some constant that I may not know yet, right? Remember how yesterday on some of those problems, we said we replaced that x plus h with like 2 plus h? Remember that? And that 2 was a number that was going to go in there later. So that 2 was some constant that was going to be inserted. But the h is the thing that's changing. The h is the thing that's shrinking to 0. Okay? So I'm going to pretend every time I see an x that it's a constant. Are you with me on that? All right, so right here, if I take this and bring it down, if sine of x is a constant, then basically when I do my limit, I can just ignore that and plug the 0 in. But wait a minute. Does this rule, the limit as h goes to 0 of cosine h minus 1 over h, mean anything to you? You had it on your test. Almost everybody missed it. It's one of those rules that's equal 0, right? If you're like, yeah. If you don't remember that, that's okay now, because if you took the derivative, you could use L'Hopital's rule, which is nice. But that actually gives me a 0, and a 0 times sine of x is 0. So that part's gone. Let's look at the other part. This cosine x is also a constant. But when I plug a 0 into that, what's sine of 0 over 0? 0 over 0. So what is my rule? Take the coefficients. So this part ends up with 1 times cosine, and 1 times cosine is cosine. Hence, the derivative of the sine is cosine. Now, that's a whole lot of junk just to prove something, but that's a proof for that one. And I could do the exact same process with cosine of x plus h. I would just have to pull out the cosine of alpha plus beta formula. And it would be similar kind of process, a little bit different, but you would end up with negative sign. So assuming those two things are true, this is an easy way to prove all the rest of them. Once I've proven sine and cosine, I could find the derivative of tangent by just rewriting it as sine and cosine and then doing the quotient rule. So to do the derivative of tangent, I'm going to do the derivative of that. Low derivative of the high minus high derivative of the low, which is negative sine x, and then over the low squared. And then when I clean this up, what is cosine squared? Those are two negatives, plus sine squared. That's another trig identity. What is it? 1. And you still have the cosine squared on the bottom. And isn't a cosine squared on the bottom a secant squared on the top? And that's why the derivative of tangent is secant squared. Now, I could keep doing this all day, but I'm not going to. So you just need to have those 6 memorized. Once they're and there's proofs like this to all of them. Once you have them memorized, we're just going to use it. And you don't have to worry about these inverse trig functions. I used to have kids memorize them early. But to do those and to show you those, you have to learn a process called implicit differentiation, which you don't know yet. So don't worry about that now. We'll come back and revisit that later. So let's just go into actual practice and see how we're going to do these. All right, now you got to be careful with trig rules or trig derivatives, because it's not always going to be a really basic looking trig problem. Like you can see right here, this was just not sine of blah, was it? It was sine to the 4th of blah to the 7th. Well, there's a lot going on, and you can see, look at that derivative. That's a monster. All right, so here's the first thing you need to understand about powers. People mess this up a lot. So let me just talk about this. If I have a function, I'm going to give you a very basic one, which is sine cubed of x. And I'm going to write also f of x equals sine of x cubed. Now, can you see that this 3 is definitely only on the x? And then when you're done, you're signing it. Well, this 3, people look at it and go, well, it's only on the sine. It's actually on the sine of x. And I don't know why mathematicians seek to torment high school students. It doesn't bother you after a while, but this right here really means this. The whole thing, the whole sine of x, all of it cubed. Not that, but all of it cubed. So with that in mind, if it means that, what is the outermost function? The 3, the sine, or the x? The 3. Even though it doesn't look like the outermost function, it looks like the innermost thing when you look at it. But it means the outermost thing. So if you're doing a derivative here, the first thing you're going to deal with is the 3. And everything else is a blah. So what you want to do, I'm guessing in your head, is you want to go 3 blah and then put a 2 on the outside. But we don't write it like this. And if you're thinking, but can I? No. You'll get better. You'll figure it out. You'll be fine in the end. But right now, you need to think like it's this. So instead of writing 3 blah 2 and putting the sign in there and then continuing, what we're going to do is this. 3 blah 2. You with me? That 3 is really on the outside. It just doesn't look like it's on the outside, but it means that. So you're doing the power rule. You really are doing this. 3, copy down the blah, squared on the outside, and then you go to the derivative of the inside part. But you don't write it like this. That 2 there belongs right on the sine. So you're going to go 3 sine 2, copy down the x. That takes care of this, the power. It's like taking care of the power. Then what? Then the outermost function is the sine. What's the derivative of sine? Cosine of the blah. That takes care of the sine. Then you go to the x. What's the derivative of the x? 1. So you're finished. Over here, f prime of x, the power on that thing it's just 1, right? So you don't have to go 1 sine 0. What's 1 sine 0? 1, because anything to the 0 power is 1, as long as it's not base of 0. So you don't have to bother with that part. You go straight to the sine part and say cosine of the blah. That takes care of the sine. Then you go to the blah, which is what? Times the 3x squared. Now, if it's totally ugly, like this one right here, where there's 4 parts, there's a power here, there's a trig function, there's a power here, and there's a number of the power. You've got to make sure that you understand that that 4 is really what? On the very outside of everything. So I know it doesn't look like that, but you have to train your mind that that 4 right there is the same thing as having the 4 on the outside. So you're going to start with that 4, except you're really not starting with that 4 out there. You're starting with this 4 here. That's why I call that A. When you have a trig function, you deal with that first. Okay? So you're going to deal with that first by going, all right, 4 sine 3 of blah. The only thing changes, you're swinging the 4, changing it to a 3, everything looks like that, and that takes care of the 4. That's the A part. The next thing you deal with is what? The trig part, right? So you go to the sign because that 7 is not on the whole thing. It's only on the parentheses. You're signing all of that. By the way, make sure you understand that. Sine means nothing by itself. I mean, what does sine of an angle even mean to you? Who can tell me?
Opposite over hypotenuse.
Yeah. It's saying, hey, there's some angle out there. It's part of a triangle. What's the ratio of the opposite and hypotenuse? That's what it means. It's nothing magical. It's a ratio indicator. It's just saying, hey, there's some angle. I don't know what it is. It's that ugly expression with the 7 on the end of it. I don't know what it is, but if you sign it, that angle right there, you're going to get a ratio that's opposite of the hypotenuse. That's all it means. Okay? So, but you got to go in order. So first, 4 blah 3 takes care of the 4. Then what's the derivative of sine of blah? Cosine of blah. That takes care of the sine. And then at this point, all you got left is something we've been doing for a while now, right? So 7 blah 6. That takes care of the 7. Derivative of the inside blah. All right, let's practice it. Here we go. Start. We'll just get going. Look at classwork, homework. What do we got in here? 10:40, plenty of time. Okay, so look at this number 1. Fairly basic start. What is the derivative? Make sure you're writing y prime. So I see something minus something. So there's 2 parts. I'm just going to join them with the sign in the middle. So what do you do with that constant? That coefficient, I mean. You just drop it down and put it times. Okay, what's the derivative of cosine? Negative sign. Somebody tell me what I'm writing wrong here. What does that look like I'm doing? Subtracting. Should I be subtracting? I should be multiplying 2 by that whole thing. So what do you have to do? And by the way, if you put 2 times a negative, that's just horrible form. Okay, your calculator sadly actually accepts that. If you go 2 times a negative 3, it actually will do that. But it's terrible form. It's like chewing with your mouth open. In this country, anyway. You know, some cultures that you smack your lips and make a lot of noise. People, oh, he really enjoys it. You know, so it's actually a compliment. But here you just look like an imbecile, right? So that is bad form. Please don't do this. Put parentheses. 2 times the negative sign of x. And the derivative of the blah is just 1, so I didn't bother with it. What about the next thing? I got this minus 3 times. So what do I do? Okay, so I could put a minus 3 and start it. Or I could see that I'm going to go 5 blah 4. And I could say, all right, instead I could just go negative 15, what? So hold up. You're dealing with just the power first. So don't do 2 things at once. Negative 15 sine 4x. And that takes care of the what? The power. Then go to the sine and do what? Times cosine x. That takes care of the sine. Then take the derivative of the x, which is just 1. Yeah.
Sorry, do you have to put this sign, the 4th, between the sign and the x, or can we put it outside of the
Yes. Get it right in there where it's supposed to be. And you'll get used to that. It will not be a big deal in a couple days or a day or whatever. It's just annoying now. Okay. All right. What about the second one? What do you see there? I see a product. So here we go. The derivative is first. Now, what's the derivative of secant? Blah. Secant blah, tangent blah. So I'm going to write secant x, tangent x, and then you're supposed to go back and take the derivative of the x, but that's just 1. Right? First, d second plus second, then times the derivative of the first. Derivative of the first is just a 2x. And you can have all of these in parentheses if you want. But technically, if it's not added to something else, you don't have to have it in there, but you're welcome to do that. What about this right here? What do you see? I see a quotient rule, but what do you see in the denominator? You could, but it probably won't match my work. And I'm starting you basic. He's saying you could take that cosecant, make it a sine on the top, and you just have sine squared over x. You're right. It'd be probably a better way to do this problem. But keep in mind, I'm probably not going to give you something as basic as this. On a test, it might be sine of 5x cosecant cubed of 4x minus 1. And in that case, even if you brought it to the top, they're not going to combine together. So it's probably going to be uglier than this moving forward. So just roll with it. Probably best thing to do is probably get some practice. But do you see that there's a product on the bottom? X cosecant x. So I'm going to go low d high minus high d low over low squared. But when I get to the d low, what am I going to have to insert in there? A product rule. So let's try it. Y prime.
That's terrible.
It is. Low. D high. So there's the low. The derivative of the high is cosine x. Minus high sine of x times d low. Now, for the d low, I'm going to give myself a little extra room because I'm going to have to insert the derivative of the low part, which ends up being a product rule. So first, times the derivative of the second. What's the derivative of a cosecant x? Negative cosecant cotangent, right? So negative, make sure you have parentheses, cosecant x cotangent x. First, d second, and again, the derivative of the x is 1, so I'm not bothered. Plus second, which is cosecant x, times the derivative of the first, which is just a 1, which I don't have to write. All of that over the low squared. So x squared cosecant squared x. Y'all see how I wrote that? I wouldn't count it wrong if you wrote x cosecant x in a big parentheses squared because of the x, but it's better to write it like that. Although I got to be honest with you, my keys very well may have a big parentheses. So either way, son. What about 4? Everybody have this? That wants it? I tell you, I'm getting a little bored with 4. How about 5? That's right. Let's spice it up a little bit. Number 5, what do we got?
Well, you gotta take out that power.
So now I got to address the power first, right? So to address the power, before I do anything, I'm going to go 2 blah 1. And you don't have to put a 1. Everything else gets copied down. Now, notice I am not dealing with the trig right now. It's just a power rule. There's a chain involved, which will eventually get me to the trig. So that takes care of the 2. 2 blah 1. Copy everything else down. Now what?
Natural.
So now the derivative of the cosine of blah is negative sine of that blah. Notice I put parentheses around the negative so I don't go times the negative. It's bad form to have 2 sines back to back without a parentheses between them. That takes care of the trig part. And now I've got 3 times root x. Well, what's our trick on that? What's the trick on square roots? Double it on the bottom, derivative inside part on the top. Now the 3 is just a coefficient. So I'm going to leave the 3 there on the top. All right, it's fine. Don't bring it down. It's not stuck to that. It's not on the inside. So the derivative of the radical is double the radical on the bottom. Derivative of the radical on the top is just a 1. So I'm done. And that takes care of that. You with me? All right. How about number 6? Number 6, what do you see? Product rule? Something times something? So let's go. I've got first, or the derivative. First, so x cubed times the derivative of the second. What do I do first on the derivative? So 2 sine of 1, 5x. That takes care of the 2 times what? Times cosine 5x. And that takes care of the cosine part of the derivative times 5. So first, d second plus second, just copy it down, times d first, 3x squared. So first d second plus second d first. And if you were looking at this on an AP test and it was multiple choice, you're not going to see this. You're going to see this. And And hopefully this is not a big deal to you. You see what I did? I just went and added the 10, multiplied the 10, put the variables in the front, copied the rest of it down. And over here, just put the variables in the front, copy the rest of it down. So that's what you would probably see. And it's actually possible that they even do stuff like factor out a sine of x, or they might do something weird like, hey, I'm going to factor out sine of 5x and an x cubed, and that would leave me 10 cosine of 5x plus 3 sine. They do weird stuff like this just to be annoying. Can you see that? I factored out, oh, I can't factor out an x cubed because that's an x squared. Factor out an x squared, and they would have an x there. You see this? Just to be annoying.
You wouldn't do this. You wouldn't do that.
Again, your test is probably not going to be a lot of multiple choice. If it's some basic multiple choice, I'm not doing this kind of junk. I might simplify it to this, but I'm not going to do weird factoring stuff because factoring is not simplifying, right? PEMDAS means, simplify means PEMDAS, right? PEMDAS. There's no F for factor in there. So why people do that, I'm not quite sure. Maybe because they're setting it up in a form, like we said earlier, to solve, to set it equal to 0 and solve. So it might be important, but whatever. All right, I really want you to notice the difference between these two. Do you see it? This is a big mistake a lot of people make. The one on the left, what am I having you do? A product rule, because there's a sine of x times a tangent of 3x. What am I doing on the right side of number 8? I'm taking the sine of that. So this, where this is a product rule, first d second plus second d first, this is just a big ugly chain rule, where sine's the outer function, then tangent's the outer function, then you get to the 3x. Are you seeing the difference? The big key is, look, there's only one x there. How can it be a product if I have one x and no other variable anywhere else? So over here on 7, I am going to treat it like a product, which I'm not going to take the time to do right this second because I want to get to something a little uglier. And then on number 8, though, it's a big chain rule. So what do I begin with? Sine. So I'm going to do the cosine of blah. And I'm going to copy the tangent of 3x down. That takes care of my sine. Then what do I do? Now I got to do the derivative of what? The blah, which, so I'm now at tangent. What's the derivative of the tangent? All right, so times secant squared of the new blah, so which should be 3x. That takes care of the tangent. See how I'm working on the outside all the way in? And then finally, the derivative of the 3x, which is just 3. But here I would be going first derivative of that plus second derivative of that and calling it a day. Yep.
Would you count off if I didn't put parentheses around the 3x? Like where you have
Probably not, but it's good form. If it's just a single x, you don't need to, but I forget sometimes. So that's not something I would count off for, but I'm pretty sure you'll see it in parentheses on almost everything. All right, let me go to something else. What about 13? 13, what are you going to go after first?
That was 4.
The 4. So the derivative is 4 tan 3 of blah. So the only thing you dealt with right there was the 4. 4 blah 3. Everything else, the tan, the parentheses, the cubed, all that came down. And you're done looking at that 4. Link it times what? Now you get to the tan. What's the derivative of the tangent? Blah. Secant squared blah. So secant squared of the blah. And that takes care of the tangent. Now you're kind of home free. You just got a big power chain, right? So what do you do now? 3 blah to the second. That takes care of the 4x to the 5th minus 5. And then finally, 20x.
To the 4th.
20x, oh, sorry, to the 4th.
bonus points. Do you get bonus points?
You correct my keys.
Yeah, on your key for that one, number.
Send me a text.
That looks kind of long.
You don't send me a text, I won't remember anything. Gotta have it in digital memory.
Wait, was that one for homework or was it the book?
Like, what?
Yeah.
Right now.
So this you don't have to, it didn't look like you have to finish this. This is just some practice. Your book work is what you need to be looking at. All right? And we'll come back to that average rate of change.
Is that just the second derivative?
The average rate of change? No, average rate of change is just the slope from any 2 points. Usually the beginning and the end of the verb. It's a big deal with what we're going to do next chapter. Yeah.
I'll turn in the, like, all the problems, like, the previous tenses when we come back. 'Cause my week was messed up because of, like, sports.
Great.
So, like, when next week I'm gonna be, like, I have to go sleep earlier and stuff, so I didn't finish it. I'll, like, get it on this week.
All right.
That's like
Yeah.
tall.
So are you saying what you turned in was finished? Is that what you're saying?
I didn't turn it in because, like, I don't really have, I did the homework class worksheet, but I didn't do, like, the, from the book, like, the.
Yeah. If something comes into me a day late, rarely, I normally just give full credit. If it starts coming in there habitually late, I start giving half credit after a day, no credit after 2 days. So again, you can use your discretion on that, but that's typically what I do. And I don't take out homework a ton calculus. I don't.
Yeah.
And after the third 9 weeks, or after the first 9 weeks, I rarely take it.
Okay.
So you'll have a little bit more flexibility with other stuff you have going on to kind of figure out when you need to do stuff. But yeah, so if you want to give it to me Monday, I'm sure I'll take it. But yeah, moving forward, try to get it in there on time.
Yeah, I have all the other ones, it's just that.
Gotcha.
We just need your blessings for tonight's game.
Man, you got it.
Keep us in your prayers.
All right, no shank.
Hopefully,
Deep, long and deep, right?
hopefully not once at all.
That's right. We just scored. Who are you playing?
McAdory.
McAdory. How they look?
Speed.
Yeah, that's right.
Speed and
Yeah,
power.
yeah.
And
But usually that speed comes with lack of distance. Sometimes.
maybe.
Yeah, I don't know.
Yeah, this guy.
I didn't play for McAdory. You know who their legend is?
We got like,
Yeah, legend. Bo Jackson.
oh,
You know who Bo Jackson is? Oh, you gotta look him up.
oh, is he a NFL player or something?
Well, he's old now. He's older than I am, but he played for Auburn. He got drafted
When I saw that, I was
number 1 in baseball. No, he got drafted number 1 in football. But the team drafted him, made him mad, it cost him eligibility. And he said, I'm not gonna play. They drafted him anyway. He didn't play. He went and played baseball instead. And he was so good in baseball. He made the all-star team in baseball. He was one of the best players in football. And then he blew his hip out after about 6 years. He'll play again. So he was arguably one of the best athletes. That's him right there. He's got the shoulder pads in the back. But that's where he went to school.
That's good. Why would you tell me that?
Yeah. Yeah, well, they don't all look like him, but he was a freaking nation.
Yeah. We might. We have a receiver who's 6'7".
Yeah, it's possible.
Yeah.
But he was like a world-class sprinter. Oh, he ran a 10-1 100 meter at 230 pounds. He's a freaking nation. Like there's been very few people like him ever.
Beast.
He was filthy. Yeah. Yeah. I'm gonna take baseball bats and just crack him over his knee.
Hello.
Do it.
Ben?
No, like wooden ones. Just take wooden ones, get angry, just catch this up. Look at the videos on Bo Jackson. Crazy.
Please, I guess.